All right. Hey, everybody. Just started this recording. Today, we will be talking about calculus. And the main goal of today is to just conceptually understand how gradient descent works. So far, we've only talked about linear regression as a model. So I'll be using linear regression as an example to talk about how gradient descent works. Now, as we start learning the rest of the models, actually starting next week, I will kind of call back to the things that we'll talk about today. So gradient descent as a concept works very similarly across a bunch of different models, differences being in their cost function. I'll go over this again later. But conceptually, the way that gradient descent works is very important to machine learning because it's literally how machines learn. And it also scales to like bigger things, not just machine learning algorithms, but to like neural networks as well. They all kind of work in a very similar way. So that's the goal of today, to just conceptually understand how gradient descent works. So gradient descent works using calculus, and it's actually less complicated than it sounds. I remember when I first learned about gradient descent, I was a math major in college, and figuring out that like gradient descent was just like a first derivative felt like kind of a ripoff to me. But I'm now of the camp that it is very elegant. It's a very, very elegant solution for how machines learn. So to start, let's talk about calculus. So calculus is a massive, massive topic in the field of math, but for our purposes, we're just going to use the derivative. So what is a derivative? Derivative, and my handwriting is not the best, so bear with me. Derivative, the formal definition, or the definition that we are going to use for our purposes, is that the derivative is an instantaneous rate of change. What that means, we're going to illustrate. Let's talk about that with our linear regression. So in linear regression, we basically built a model that is able to predict, the price of a house with some features. So let's just say we have this line over here, and let's just say right here in this example, we only have price and square foot. How we're going to talk about instantaneous rate of change in a linear regression is very similar to the slope. So the slope or the coefficient for this example, let's just say the slope or the coefficient for square foot is 20. Coefficient equals to 20. What does this mean? This means that with every increase of 1 square foot, the price will go up by $20. So let's just say I have a price square foot over here. Let's just say this is, I don't even know what kind of measurement houses have. But let's just say 500 square foot gives us $1,000 house. If we have 501 square foot, that should be a $1,020 house. That's what we mean by a rate of change. So if we were to go all the way up to, let's say, let's do 1,000. Let's just say we have a 1,000 square foot house. This price over here, we will have to add 500 times 20, which is 500 times 20 is 10,000. So we'll have a $11,000 house here. So it's the amount of increase in the price as a result of increasing the square foot. This line is a straight line. It was a linear regression. So this line being a straight line, and if you think about the rate of change of price with respect to square feet is $20 per unit of square feet. And in this case, the rate of change was also constant, right? Throughout our entire range of square footage, the relationship between square foot and price that we got out of our model is that it is a constant rate of change, right? No matter what range of square footage we're looking at, whether it's in like the 500 square foot, maybe it's in like the 20,000 square foot, every time you increase by 1, the price will always go up by $20. So in our linear regression, we had a constant instantaneous rate of change of 20. So any questions about that to start? Just thinking about what we've done in linear regression as a rate of change. Actually, I didn't want to erase those. All right, let's change an example. So let's just say that we're expanding from linear regression, and let's just say that we are able to build a model that looks slightly different. And let's just say that our model looks like this to fit those points. Now, if our model looked like this, we no longer have an instantaneous rate of change. Because apparently between these values over here, the price actually goes down when you increase your square foot, right? And like at, let's say maybe at like these, I don't know, let's just say in this region over here, maybe it doesn't make sense to keep increasing the square foot of your house. But after like about $1,000, you should increase the square foot of your house. Maybe between these ranges over here, you should increase the square foot of your house. So it's a non-constant rate of change.
Excellent.
Why is that relevant for us to know? We want to now think about slope. And now we talk about instantaneous, the fact that it's instantaneous. When we had a straight line, the rate of change was the same throughout. So the fact that it's instantaneous didn't really matter. But in this case, it kind of does. And how do we measure this instantaneous rate of change? We use what is called a tangent. This is all very, very abstract for us. Like we don't actually have to do this drawing, but let's just say as an example, what is the instantaneous rate of change over here? If we were to take a straight line and draw it across, the slope of this line is that instantaneous rate of change. If we were looking at it over here, you can see that the straight line would be kind of sloping down. We would actually have a negative rate of change. What is it relevant for us? We're actually taking a look at, actually, we'll get to that later. What I also want to talk about is what about these points over here, where the relationship kind of changes. At these points, our rate of change actually becomes flat, right? Anytime you have like a change of direction, your rate of change becomes flat. So even here, our rate of change is flat. That means, let's just say that this is a particular value of like, I don't know, let's just say 600 to 601. If we're increasing our price from 600 to 601, there is no change in price. So why is this relevant for us? Because if our rate of change is equal to 0, it usually signifies some sort of minimum or some sort of maximum, right? Because at this point, this is a maximum point over here, and this is a minimum point over here. And for optimizing things, it's sometimes useful to know where we can find this minimum or maximum. So we're going to go off of this when we start talking about gradient descent. Main points from what I just talked about in the last 5 or so minutes is that if you have a line that looks, or a curve that looks like that, at different points of the curve, you're going to have different rates of change. And also wherever the derivative is 0, and derivative being the slope, you have a minimum or a maximum. Questions about any of this? Okay, so this is like super crash course in calculus. So let's clear all of this. Let's next talk about gradient descent.
Oh, let's go back.
Here we go, gradient descent. Okay, so gradient descent looks at the derivative of a cost function. So we are looking at derivative of a cost function. So every machine learning model has an associated cost function. And it's directly related to how this machine learning model learns. If we're thinking about linear regression, what was linear regression's cost function, right? How does linear regression decide what the best line or the best coefficients is? It's using the cost function of your least squares, whether it is your mean squared error or your residual sum error, many different names for it, but pretty much the same thing. In a linear regression, and let's just set up a linear regression like this, and let's just say we have our data points over here, 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 and here. For any line drawn through your data points in a linear regression model, our cost function is going to be these distances over here, the sum of the squared distances over here. That's going to be our cost function. So if the line doesn't fit very well, you're going to have a high value of your cost function. If the line does fit well, it'll have a relatively lower cost function, value of cost function. Questions about that? Okay, I'm going to take it quite step by step today. I think it's really important for us to know. Okay, so for linear regression, our cost function was determined by where, our cost function is defined by the residual sum squares, or the distance between the points of the line, and the whole goal of ordinary least squares, or OLS, or linear regression in general, is to reduce that error as much as possible. Scikit-learn takes a gradient descent process of solving linear regression. This is different from what we talked about yesterday. Yesterday's stats models actually uses the linear algebra way of solving it, but today we'll talk about the scikit-learn method of solving linear regression. So how does gradient descent work? There are actually a few steps for gradient descent, and we will kind of outline them on this side over here. Okay, so first off, you have to know your cost function. So when we talk about our other models throughout the rest of this phase, I'm going to mention what the cost functions are, and then how they are optimized in their gradient descent processes. Next, you start with some initial values. So with initial values, let's just use this as an example. I wanted to erase these lines over here. So let's start with some initial values. Initially, let's just say we don't even know where to begin. Oops, I want to draw that next second. We don't even know where to begin. Let's just start at 0 for everything. So with 0 for everything, our line actually looks like this, straight across the bottom like that. Obviously, that is not a great line, but we can still compute a value for the cost function. So we're going to take this error, and as you can see, there's a lot of error. So with that, we're going to actually record what this error value is. And we're actually going to have another graph here on this side, and we're going to take into account what is our cost function. Cost function, and then let's just say beta value. Beta value being like the slope. Let's just say we're trying to compute the slope here. And in this case, this is price. This is our square foot. And this is our cost function, and this is our beta. Remember, beta is the slope. So at beta equal to 0, this green line, the slope of this green line, we have a pretty high cost. So let's just start it at over here. Let's just say this green X is the value of our cost, relatively high. Now, next in gradient descent, you're going to usually define some sort of learning rate. And learning rate we'll talk about as we get to the next step of our gradient descent. But there's a learning rate, which basically will tell you how much to adjust your parameter values. So for example, let's just set our learning rate as arbitrary for now. But based on this really poor error, it usually tells your model, how should I improve? So with that learning rate, which we'll get back to in a little bit, maybe it decides, okay, for my next line, let's shift it a little bit up like this. Cool. So with this line shifted, actually, let's start not as good first. Let's shift our line a little bit this way. Cool. Now that it's shifted like that, we can compute this error again. So now these yellow distances, as you can see, are already shorter than the green distances. So the overall cost is going to be a little bit lower. And let's just say that this is a different value. So over time, with your learning rate as well, your line is slowly going to shift and get better and fit the data. So let's just do one more. Let's just say this blue line is going to be there. And we measure the cost, and let's just say that the cost is around here. This is a general, this pattern of seeing the cost go down as you shift your parameter is usually what you see in a cost function graph. So you keep going, and at some point you're actually going to overshoot. You might overshoot, I would say. You might overshoot your line. So let's just say at this green line over here, we start to go up again. And so the whole idea of gradient descent is gradient descent will actually recorrect your overshooting. So if they see that it's shooting up, then they say, okay, it's probably not the second green line. Let's go back to our blue and adjust it a little bit less. So if you keep doing that, your cost function and this bottom right graph is going to slowly fill up and look like this. And at some optimal point here, this is the beta that you want to choose because your cost function is the absolute lowest. Does that make sense? Cool. So what have we done here step 4 is your cost function usually gets better. Cost function gets better. And you can find the best beta. Cool. So all in all, what have we done? If we want to find out this part over here and calling back what we did when we talked about, calculus earlier and taking like the minimum and maximum, this value over here corresponds to where the derivative of the cost function is equal to 0, right? Because at this point, the slope of the cost function is 0 and it's a minimum point. And so because of that, that's why the derivative of the cost function is important. And the derivative of the cost function, if you go into the math, and this is specifically for linear regression and a couple others, but specifically for linear regression, you can actually take the derivative of your cost function, figure out where that is, and that will give you your best beta value. But conceptually, what's happening is we're just shifting our line up and down, and where we shift the line is dependent on our learning rate. We're shifting our line up and down until we can get the lowest amount of error for our model. Any questions about this like overall concept of how this model fits? Okay. So if you've noticed, this point, this graph of where we're fitting our best line has been anchored to this point over here. Because as we know in a line, there are two main things that we're shifting, the different slopes or the different coefficients, or the intercept term. So as we know, the intercept term just shifts the line up and down. So let's just say, okay, this blue line is the best slope. Maybe we can get the best intercept as well. So what we'll do is the blue line will shift parallel up and down to see if we can fit the best data. If we are shifting the line up and down and we're shifting the line back and forth, is eventually going to find the optimal parameters across the board. So this actually does scale up to multiple features, right? In your linear regression, well, y'all had at least 10 features at least. And so they're actually doing this across all dimensions at the same time. And that's where linear algebra kind of comes into play. This is where partial derivatives, which I don't think is important for y'all to know how to compute, but just understand that this process does scale to multiple dimensions as well. Cool. So with that, let's talk a little bit about this learning rate over here. So learning rate is something that you can set in several models. For linear regression, I don't think that is a parameter that you can set, but we'll actually see a couple of models next week where you can set this learning rate of how much should I adjust my parameter to figure out what the best values are. And there are some pros and cons to different learning rates. So let me actually clean this up so it's not so messy. Okay, so a typical cost function, and actually let me clean this too. So a typical cost function has this kind of shape. Oops. Typical cost function looks like this. If your learning rate, and let's say you start over here, if your learning rate is high, you get there faster, kind of, right? Your learning rate is high, you immediately will skip from here all the way down here, and then you'll maybe overcorrect and eventually arrive to your minimum. If your learning rate is too small, you'll slowly traverse down this cost line and then eventually get to your minimum. Now, when you really have to worry about learning rate is when your models get really big, or if your data sets get very big. If you have a lot of rows, if you have a lot of features, because the learning rate is really going to help optimize the amount of time it takes to train your model. For this upcoming phase, it's probably not going to matter so much. If you find that your models are taking a long time, maybe increase your learning rate. But with a high learning rate, just know that it is possible to overshoot your minimum. So if we just go backtrack over here, let's see. If you have a high learning rate, let's say you start over here, it is very possible that you set it too high, it jumps over here to this point, it's going to have an overcorrect itself, jump back here, and it might take even longer. So there is kind of usually a sweet spot for learning rate. That is something that I will show you all how you can tune and adjust for later on this phase. But learning rate is one of the more important components of gradient descent because it kind of determines the speed of, the descent of your gradient and also how it figures out what the best parameters are. Cool. So even though we talked about this in the context of a linear regression, all machine learning algorithms work this way. Every single algorithm that we're going to talk about, with the exception of 2 that we're going to talk about the following week, every other machine learning algorithm we're going to talk about works this way. Not all of them have like the mean squared error as their cost function, of course, because different models work differently. But when I mention a cost function, I'll briefly talk about how the gradient descent process works with that cost function for that specific model. But yeah, that's pretty much the process of gradient descent. Does anyone have any questions or thoughts about this process? Because this is pretty much the basis of machine learning. The fact that it slowly corrects itself such that it lowers the cost function or lowers its error as much as possible.
So does it always anchor the beta at the origin first, or does it actually just do both at the same time, or is that just how we learned it first?
Good question. Yeah, good question. Yeah, this anchoring is just to simplify talking about the process, but yes, it's actually doing all the parameters at the same time from the get-go. Cool. Anything else? All right, just to set the expectation of how much of this is important to understand. I have been asked in the past, like interviews, how does gradient descent work? And so I think if someone asks you this question in an interview, usually an answer that suffices is you can say, all right, well, it depends on your cost function. You usually initialize some parameter values, and based on a learning rate, your parameter values will keep changing, and measuring the cost function, you'll eventually optimize your best parameter values, and that's how your model trains. Usually something along those lines, of course, more refined, will be good enough. Only one time ever, and I will say it was for a very, very technical position, I've been asked to hard code the process of gradient descent, which was actually in your pre-work as well. You will likely never have to do something like that. But just conceptually understanding what's going on when you are training a machine learning model and why it sometimes takes so long, it's helpful to know. Cool. For this topic in your labs, there are a good number of labs that have you hard code a lot of things. For now, to be honest, I don't think it's that important for you to be able to hard code gradient descent, because at the end of the day, when you're implementing any of these models, you will never have to hard code these processes. Again, it's really more of a conceptual understanding of what's going on, and that will be good enough. But yeah, I think narrowing down this topic to just understanding how gradient descent works is the main point of this. Any other questions? Because that's kind of all I had to share for today. We still got half an hour. Any questions about anything at all?
Some question I already forgot. So the cost curve is based off the derivatives of the residual sum of squares, correct? Or
The
is it just
cost
based
curve is literally the residual sum of squares.
Okay.
The derivative of the cost curve comes into play when you're trying to figure out where the minimum actually is. So what it does is, okay, with a bunch of these points, as you slowly populate these points, it's going to build this cost curve, and it's going to start to compute, okay, at this point, all right, this is the derivative. Oops, let me use a different color so it's clear. This is the derivative right now. Okay, well, maybe we're here, this derivative, maybe it overshoots here. Oh, okay, we've kind of overshot, let's go back. This is the derivative. So that's when the derivative is being used to figure out whether where you are at is a minimum or not, or close to a minimum or not.
And this is just a much faster way to find our coefficients, correct?
Yes, actually it is. It is a much faster, well, that's actually a good question. If you compare this to OLS, like in stats models, when you scale, this becomes a lot faster. When you have small enough matrices, sometimes the linear algebra way is faster because you're really just multiplying matrices. You're not doing processes over and over again. You're not calculating, gradient, the cost curve at every single iteration. But when it scales, because if you imagine in linear algebra, when you're multiplying matrices and you're doing all of that computation, that does not scale very well. And you're storing a lot of unnecessary data. So at large, gradient descent is a lot more efficient, both memory-wise and also time-wise, versus using matrices to solve.
Perfect. Thank you.
You're welcome. Sweet. Anything else? Okay, I do highly recommend that. Like, just sit with how gradient descent works. There are a bunch of really useful like YouTube videos that also explain this in much more detail than we have time for. And I think understanding how gradient descent works will really set a good foundation for understanding all of the models that are to come. I'll tell you that like the next study group that we have, we're going to go straight into a brand new cost function. Well, not brand new. It's actually going to be very similar to this one, but slightly different. And we're going to see how to help overfitting in linear regression. So that's going to be pretty exciting because we actually get to finally talk about it in terms of the machine learning cost function. So yeah, cool. Well, if anyone has any questions, feel free to Slack me and let me know. I know this study was a little bit shorter because it's really just this concept that I think is the real important thing here. If you already have an understanding of calculus, I wouldn't spend the time going to like hard code a derivative formula. I personally don't think that that's going to be a good use of time. I'd rather you spend the time getting comfortable with conceptually the idea of gradient descent. All right, cool. Well, feel free to let me know if y'all have any questions. Happy to talk about this more at one-on-ones. But as we do get to more and more models, I think that the idea of gradient descent will make itself, I mean, the versatility of gradient descent at least will be more apparent then. But cool. If there's nothing else. Oh yeah, were you saying something, Sam?
I'll just say thank you.
Oh, all good, all good. All right, cool. Yeah, if there are no other questions, Slack me if you have any problems at all. But if there's nothing else, I will see you all back here next week. All right, bye everybody.
Bye, everyone. Have a good night.
Good night.